Hello everyone, welcome back to another organic chemistry video. This video is for those of you who know most of the reactions in Organic Chemistry 1 and want to do some synthesis practice problems to either better understand them or to prepare for an exam or something where you're going to have to know how to do synthesis problems. So if you know the reactions, they can be quite stimulating. So for this first one, let's say that we were starting with this molecule and we want to make one that looks similar, but we have this. So how would we go from this to this? So go ahead and pause it and think about it for a few minutes if you need to. So I'm going to explain this step by step. So first, we're trying to get an aldehyde on this right here, right? We're trying to get it on this. The oxygen of the aldehyde is on the terminal carbon. So if we want to place a group, we'd preferably want to do it at that terminal position, terminal carbon. So we can't quite put an aldehyde there at the moment because there's a double bond. But you can put a hydroxyl group there, right? You can put an alcohol there. So the way which you can do that is by hydroboration. So BH3, THF, these are the reagents for hydroboration simply. And then it's like a basic conditions. You want to put hydrogen peroxide. You want to use water there as your solvent. So then the outcome will be that there's going to be an alcohol group, an OH on the less substituted carbon. So not on this carbon, but on this carbon. Right? This is going to be the carbon we're going to put the OH. Then we want to go from having an OH there to having a aldehyde there. Now, if we use this process is oxidation. So if we use a strong oxidizing agent like chromic acid, this would go fully to a carboxylic acid. But if we want to make it from primary alcohol to the situation where we have an aldehyde, you want to use a mild oxidizing agent, and there you want to use PCC. Okay, so that will do it. Hydroboration and then PCC. Okay. So let's go over the next example problem that we're going to do. This one is, we're beginning with the same molecule. Let's draw it right there. But then we're trying to get to a ketone. So what would we need to do in this case? First, notice the ketone, this little oxygen double bonded, is on this carbon, and this carbon will correspond to this one on the beginning structure. So it's on the more substituted carbon of the alkene. So whatever group we want to add to this alkene, preferably it should be here, so that then we can edit it and make it into a carbonyl group like that. So we know we can add alcohols there fairly easily. The way we can do that is by either two ways. You can add mercuration, the oxymercuration process, which looks like this. Let me see the reagents on this, so the first one is Hg, and then acetate, and with water, and then you would have for step 2 demercuration. Right? So you use this. But mercury is toxic, so you could also use just acidic hydration, where you just put acidic water, right? And preferably with sulfuric acid. So either way can work. With the mercuration, you might actually get less, side products. But it really doesn't matter for these problems. If you put this or that, it would both be correct. So that's the first step. Then the result of the first step is that you put an alkyl group on this carbon. To make that a ketone, we can either use a strong oxidizing agent, so we can use something like chromic acid, which, what does chromic acid look like? I think it's you can either write it like that or you can write like this. It means the same thing. Now, if you use chromic acid, this secondary alcohol will be oxidized to a ketone. However, you don't necessarily need to. You could also use PCC, which we used before. And PCC is a milder oxidizing agent, but in this case, it's taking it one step up, right? Because in oxidizing, you first have an alcohol, and then you can use PCC or you can use chromic acid, and you can make it a ketone, right? But then if you use chromic acid, it would actually take it all the way up. It would have taken it all the way up to a carboxylic acid, but in this case it just ends at a ketone. So either one work, and I think it's better to use the milder one in cases where you could use both, just because it's less toxic, less dangerous, and so preferably you'd want to use these two, but for green chemistry purposes. But you can also have done with the mercury and with chromic acid, right? Either way you get to that product, you are always going to have side products with these. Okay, so then the next problem is looking like this. We have a 6-membered ring, and we want to end with another 6-membered ring, but this time the alkene is gone, but we have a bromine here. So how would we achieve this? So in this case, it's actually kind of straightforward. What you can do is to add a halogen to the less substituted position of a am I drawing this correctly? Yeah. You just want to use bromine with peroxides, and you will simply get that answer. Alright, so that was simple. Now, another situation we have here, we want to convert this molecule with a double bond in the middle into this molecule. So go ahead and think about this. Notice in general the differences. So we have a double bond in the middle of the molecule, but here the double bond is gone, but on one side of it we have a methyl and we have a hydroxyl group. So how about we add those? First, you can get rid of the double bond and add something there. You can get the hydroxyl out of the way, right? So you can just put a hydroxyl there, and the way you do that is, let's say the double bond goes away and we have a hydroxyl. You can do that using any process, so we're going to use acidic hydration for this example. But you could also use hydroboration, which is the BH3 thing, or the oxymercuration, demercuration, which is Hg and the acetate. But in this case, we're going to use acidic hydration to get there. You might notice that the hydroxyl can go here, right, or it can go here. But either case, the molecule is symmetrical, so it's going to look the same. If the hydroxyl were here, it'd be the exact same. There are 2 carbons to the right on the edge, and then here, in this case, there's also 2 carbons on the edge, and 3 here. Now, we want to add a methyl group to this carbon. Right? There's a methyl group missing. How would we go about doing that? To change the carbon skeleton, you can use Grignard's reagent. But to add Grignard's reagent, you need an electrophile in your molecule. So we need a good electrophile. Therefore, we're going to actually use PCC to oxidize this to be a ketone. Now that we have a ketone, this carbon is a very good electrophile, right? This is a slight positive charge. And you can partially attribute it to resonance as well. So then, to go from this molecule to the desired product, we need to use Grignard's reagent, which looks like this. So this would be a 1 carbon, and then it would have a bromine on it, but then you want to add magnesium and ether to it, and what you would get is a molecule that looks like this. You have a negative charge on the carbon atom and a positive charge on the magnesium and the bromine atom. And so this negatively charged carbon atom, this carbon nucleophile, is going to attack over here on this carbon, and then it's going to push out the electrons here, and you're going to get this methyl group attached. Now at the end, your oxygen molecule has to be protonated, so you'd want to add this reagent first, and then you'd want to add perhaps just water or acid to protonate that negatively charged oxygen atom. So the last example for this video is going to look like this. Go ahead and try to convert this molecule into this one. So in this case, again, we're modifying the carbon skeleton, and every time you're doing that, not every time, but Grignard's reagent is very useful. But again, in order to have a good Grignard's reagent, you want to have a good electrophile in your molecule. So to get an electrophile here, we can again use PCC to oxidize this into a good, nice looking ketone, or in this case aldehyde, actually, not ketone. So we get an aldehyde as opposed to a OH alcohol group. Then we can use Grignard's reagent. So in this case, we're adding 1, 2, 3 carbons to the chain. So we want to use a 3 carbon Grignard's reagent. So this carbon, terminal carbon, would have a negative charge, but then it's kind of being stabilized by this magnesium bromine combination that has a positive 1 charge. So this is going to then attack this carbon and push out the electrons, and so we're going to get so 1, 2, 3 carbons, right? And the shape of it looks a little bad, so let me redraw that. And then I didn't show this in the last problem, but if you want to protonate this, you can just use an acidic water, like this, or you get hydronium ions in the solution, and it would simply protonate the oxygen, and you get this as the outcome. And so I hope those were, challenging enough, but not too hard. So thank you for watching.